get started, I guess. Thanks for inviting me. I got an email a couple months ago, or a month or two ago, that said we have an education thing, and I've been out of the ham radio world for a couple years, and I thought it'd be fun to come to a field day again, and why not sign up? And I remember a couple of field days being with some friends who were new to ham radio and digital stuff, and not really having a computer science background, and wondering a little bit more about like how these radio signals convert to digital, how the digital stuff works, and from a computer science background that I'm coming from, and also as a software engineer, I think a lot about the zeros and ones and the encodings and the protocol stacks that build up, and the character sets and things like that. And for me, it's kind of fun when I'm seeing something happening in digital, because in the back of my head, I'm thinking about how all these things connect. So the thought that I had was to share a little bit of that perspective of how we got from analog signals up to zeros and ones, up to like representing data, and the kind of stuff that we can share digitally over the air. And this Saturday morning crowd might be already kind of in that world, so I don't know how many people that we've got here maybe on the recording, though. Hopefully we'll enjoy this. But at the same time, there's a little bit of back to basics. Like, if we can pause a step and go back to the basics and think about those things, I think it can help us have a more enjoyable hobby, and also maybe not treat things like the APRS protocol so like locked in stone, or things like message formats and protocols that we use for MCOM and whatnot. Going back to, like, if you've seen the ARL radiograms that are like treated like like some Ten Commandments handed down in stone, like we've got to do this. It's not that those are bad, but it also, if we have the flexibility to understand what's happening, I think below that level, we also have the freedom to explore and innovate and invent, and also not make some of the mistakes that we make. So I have this pseudo PowerPoint that if someone would like to follow along, I have one extra copy. You're welcome to come and take it, but I think we're close enough. You can probably see these. The idea starting out is the signals that we have coming through the radio waves are in an analog format. So the wave is not like, it's not sending zeros and ones through the air, but it's kind of this signal that, in the sine wave pattern here, that's what an analog signal looks like. If we want to use digital, we need to convert that analog signal to something that looks a little more square, like a 0 and a 1. In this case, the 1 signal is a +5 voltage, right? And the 0 is a 0 voltage. But that same type of interesting thing, like, I don't know if this is large enough, but there's a concept that as a analog signal is coming through the air, we want to sample that signal and pick out whether it's a high or a low, right? And the way that sampling works is interesting, right? Because if you sample that signal at a rate that's too slow, you might catch like one signal up here and one signal down here, like later, that's at the same level, and it might even look like a straight line, right? Because you didn't sample fast enough to catch the low, the high, and the low. So the sampling rate is interesting in digital, right? That little point in time that we caught the analog signal. And you'll hear these terms ADC and DAC. So the ADC is analog to digital converter, the DAC is digital to analog converter. And this graphic kind of represents, okay, I'm taking a little sample of that and I'm putting it into a digital format, but like these lines on the initial sample, they're still kind of herky-jerky, right? It's not a smooth curve. So by processing some of that data, you can then turn that into what looks more like a curve, and then you could convert it back into like a really clean, mathematically clean curve that you really didn't have even in the real analog world before. But in this processing, that's where there is a lot of room for computers to kind of mess up or not be exact or whatever. But that's the essential thing. And so in a lot of these digital modes, the sampling rate, and that's kind of the magic of getting some of that. One question I guess I would have for the group, since we're, 6 people? 7? Would you consider Morse code to be an analog mode or a digital mode? Yeah. It's pretty much digital, even though it's interesting because CW continuous, right? But it's it's kind of our brain converting analog to digital, because we have a wave that's going on and off, but it's going on and off in a 0 and 1 type of pattern. So you could treat the dots as one and the dashes as another. So it's kind of this initial binary code mode. I think all of the digital modes that we have on top of that are kind of like that, but just to a much higher degree. Okay, so now this is where we divert a little bit from, and again, this is going back to basics here, but let's say we do manage to pull out a 0 and a 1 signal from that wave. Now we really get to start treating it as like a digital format. And so this is an example of like a binary byte. So each one of the zeros and ones are a bit, and 8 of them together make up a byte, right? So that's the bits and bytes of radio. And in this representation, if you wanted to like convert this number of zeros and ones into something like a number system that we're more familiar with, for example, base 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like if we're converting it to a number system that we normally use as humans, the way that this works is think of, this is where it's going into math a little bit. The base 2 number system only has 2 digits. It has 0 and 1. So if you want to represent the concept of a 2 in base 2, like the digit 2 that we're used to in the base 10, we actually have to use 2 characters. So this first character is either the value of 2 to the 0. So 2 to the 0 is 1. We can either have 0 or 1. 2 to the 2, or 2 to the 1 would be 2. So if we're adding up 2 to the first power plus 2 to the 0th power, we get a 2. So this 0 tells us yes, we want, or this 0 says no, we don't want to count 2 to the 0 power, so that's going to be 0. The 1 says we do want to count 2 to the first power, 2. And then on this side, we're just adding up all these values. And if we keep that process going, down to 2 to the 8th is 128. That one wasn't represented, but we did have a 2 to the 32 power. So adding that all up gives us a number we recognize, like 42, right? So this is the house of cards that we're building as we do these digital protocols, because we need some way to mentally like make sense of these zeros and ones. But we don't just talk in numbers, we also talk in letters, right? So actually, before I go to that, so nobody can cheat because these are small enough, you probably can't see them from where you're seated. What would 1101 in binary be in base 10? Anybody willing to give this one a shot? 13, very good. Yes. So that's basically just doing that addition. So this chart also shows, and this is a concept that I think some of my friends who maybe didn't have that digital background, like there's also a number system called octal, and that's base 8, right? It only has 8 digits. And then there's hexadecimal, which has 16. Instead of like what we're used to counting up to 10, we in hexadecimal we count up to F. We ran out of numeric digits, so we add A, B, C, D, E, F to the end of. My call sign is Alpha Delta 7 Foxtrot 87F, and one of the things I like about that call sign is it can be represented in hexadecimal. It doesn't need any character after the letter F. There's a chart here that kind of shows a binary representation, a decimal representation, and then a character representation, like an alphabet. Well, to be able to have an alphabet, that a number, this number is going to represent this letter. And so one of the standards organizations, one of the standards that we use for characters that's probably the oldest and most consistent, probably a little newer than Morse code, but not by much, is the ASCII character set. So American Standard Character Interchange, something like that. So ASCII, ASCII, is the conversion that we use for, it's basically agreed that like the very first numbers are a set of special characters, and then we have like at 65 we have the letter A starts, it goes to 74, and then interestingly at 97 the lowercase letter A starts. So when you're working in ASCII, you actually have to think about case sensitivity, right? Is it an uppercase or a lowercase? But 8-bit ASCII codes allow 255 different characters. Since that's what can be represented in 2 to the 8th. A conversion, if we wanted to go from binary to text, we could take, basically we could split up each one of these sections, convert it to the number like we did before, and then convert the number to the letter. And so the nice thing about digital modes and computers is they can do this all, automatically, and we get what we see as letters kind of coming through our screen. I think for a lot of people, and maybe those of us here will have a chance to kind of share this with other people who might be struggling to, like, how do I get into this digital world? Like, these are concepts that they might be able to grasp and be like, oh, cool, okay, I get it. The Unicode character format is like ASCII, but, well, what's different about Unicode for those? That's got to be main difference. Unicode, so ASCII had, like, we could represent that in 1 byte, 8 bits. Unicode takes, like UTF, well, like, it can take 4 bytes, right? So in this example here, I've got like an ASCII encoding, just the number 48, right? 48 in hex, sorry, would be the capital letter H. Well, in UTF-8 in hex, we would have 00000048. It's the same number. It's the same hex number in in Unicode for that letter H. Like, it shares that first part of it, but you've got these 3 extra bytes that Unicode can use, and that's why, like, the Unicode goal is to be able to represent every glyph, every character in the human language, in every human language across the world. So that's why you get, like, even emojis and different alphabets. The reason it can do it is simply it has more space. It has more bytes. The downside of that, of course, is it takes more bytes to represent. So every single character is taking 4 times as much. But this is a world where, like, when we're getting into decoding, it can really twist your brain. And, like, the smartest people can get tripped up in, like, these layers of encodings. And Unicode is also fun because it has some bytes point you to different code points. You can look it up online if you want to drill into Unicode. So that's kind of text sharing over encodings. With digital, we also get to graphics, audio, video. A really fun part of the digital formats is when you're sending a digital file to someone, that is a binary file, but it also has its own encoding. So lots of different graphic file formats compete with each other because they have different characteristics of how they assemble the zeros and ones. So name some graphics file format extensions, like file formats that you might have heard of. JPEG, PNG, PDF, GIF, GIF. So I remember in the 80s, a computer and a modem that connected me over the phone. Doing this, well, the modem modulator, demodulator, it's doing this analog to digital conversion over the old school telephone lines, same as we're doing over the air here. But I started hearing, as a teenager, I'm hearing words like protocol and GIF or GIF, which one, and in that day they had protocols called X modem, Y modem, and different things that were designed to convert these, like, signals into binary files. And one thing that was really precious back in those days, and it still is in amateur radio, is the like the bandwidth that we have, because we don't have, like, back in those days, we didn't have gig Ethernet coming to our house through Comcast, Xfinity, or whatever. You know, we had 300, 1200, 2400, if you're really cool, 19.2K compression, like speeds. And so the digital image formats that are getting shared back and forth, the size of the file is critical, because the bigger the file, the longer it's going to take to transmit. So that's where, like, the image formats have a term called lossless and lossy compression. And one of the neat things about the lossy compression algorithms is it takes advantage of our human ability to see something and make, in our brain, make the same image out of what we're seeing, or at least we get an idea of what we're seeing. This probably doesn't look much different to you from where you're sitting, the bottom one. This is a picture of a dog at 824 kilobytes, so almost a meg. 50% lossy compression brought that down to 76 kilobytes. So the space on disk or over the network, over the wire, over the air, was significantly less. And this one, 80% lossy, also like brought that down to 38 kilobytes. So I think in like emergency communications or others, especially where we're limited by bandwidth speed, there's actually some people I know who are just like used to just sticking whatever file they can on their computer and having that get to the other end, but a little bit of compression in the right place can do just the same like job. This top picture is a picture of a hand, and you probably can see the difference there. This is actually 90% JPEG compression at 56 kilobytes, and this is the PNG format at 63 kilobytes. So 63 kilobytes and 56 kilobytes, not a big difference. In this case, taking that PNG format would be a much better choice than the JPEG format. So even within the different formats, as it goes to video, the video formats also do a similar thing. Like the MPEG video format will take advantage of the fact that one frame to the next doesn't change very much. So as you're taking, multiple pictures in a second, during that 1 second, all the pictures are pretty much the same except for maybe the person's lip moving or whatever. And so by sending just the differences between each frame, it can lower the amount of space needed to either save that file or to transmit it. Another thing that I found kind of really fun to watch lately is Google and Facebook competing with each other over audio codecs. Even though this isn't 100% like the stuff they're talking about isn't maybe to the they're not necessarily targeting their publications and research wins and stuff to the amateur radio community, but we use audio codecs in our digital modes because what the digital modes will do is they'll take a stream of zeros and ones and convert that to something that our ears hear as the audio. And so this is where the title of the talk that I submitted, Beep Boop, comes in. A lot of times all over the air we'll say R2D2 also, because it starts sounding like R2D2 instead of an actual human voice. That's because the data bandwidth has suffered so much that as these audio codecs are trying to translate, they just don't have enough. They don't have enough to make it into a meaningful signal, but they still share what little they can. The Inside Out, the second Inside Out movie just came out, and we watched it, but it reminded me of the first Inside Out movie. So this is the Disney movie where they're going through, and they enter into a world of abstract, like, thought, right? And all of a sudden their 3D world turns into like this 2D world with just really abstract symbols. And sometimes our protocols do that to us as well, because it's like we're so constrained that it like just relies so much on the human brain to make up the pictures. But one cool thing about these the new audio codecs, ham radio has run into some drama because some of these codecs are proprietary, even though we want to be all about like openness and documenting everything in ham radio so other people can build on them. Some of the codecs are open source, but they're usually not so great. Like there's one called FreeDV that's being developed. They're really cool because you can see the source code to them on GitHub and other places. But one of the cool things these big companies are like Google and Facebook researchers are doing is they're using neural networks to take they're training their machine learning. They're using machine learning and AI to train signals coming in to create a converter, and then they use the codec that gets generated wasn't some really smart person like figuring out how to build some new algorithm. It's actually the machine learning generating that little piece of code that's going to do the high-speed conversions. And one of the things that this code is kind of cool, writing code this way using the machines is kind of cool, because by putting that computation power into the development of the codec, they can reduce the computation power that's needed on the later on. So that way, like phones and other devices with less amount of computing power can do the computing necessary to convert that stream of zeros and ones into audio that our ears hear. And it's really interesting that these codecs that our phones use don't actually give us back the same like audio signal, but they give us a signal that our brains perceive as what the other person is saying. So that's kind of a fun thing about audio codecs, and I think we're at the 9:30 mark here. I wanted to kind of mention, just to kind of bring some of these concepts back home, the APRS protocol that we use in ham radio. You can see these like frame diagrams if you go online, and they'll have a number at the bottom. That's the number of bytes that represent like some piece of this protocol. And so by going back to our zeros and ones, right, and our bytes and our character representations, that's what APRS and other protocols are built on top of. And feeling confident in your ability to convert zeros and ones to characters, I mean, it might seem like it's really down in the weeds, but it gives you the confidence to actually understand how APRS is working. I mean, on top of those frames, then you're going to start seeing characters that mean special things in APRS. And then you're going to get like a raw APRS packet that you might see fly through. And then, like, on top of that, the commas and the different codes that mean things, right, decode into something, latitude and longitude or otherwise. And I think, like, if we do take the time to be fluent in being able to walk up and down that stack that gets created, we also will be able to have the freedom to and ability to develop new protocols that do even better. and we'll be able to call out problems in protocols that, like, it was handy for someone who was just being a hobbyist, but it's not feasible to scale out to everybody using. And basically have fun talking about that. So thanks for coming. Off to a great field day. Thanks, everybody. Thanks, Matt.